In this tutorial, we're going to be covering deep learning, where we're going to learn just a little bit about it, because we've already covered this topic a little bit, and then we're going to end up coding it. So the topics for the slides will be pretty brief. We're going to cover wide versus deep models, followed by some use cases for deep learning. And then we're going to have a quick refresher on the vanishing gradient problem. After that, we're going to move on to the actual code, where we're going to create 3 different architectures and compare the performance of them. We're going to use dense layers instead of convolutional layers. That's really so that you can have overall faster processing times, especially for those of you out there who are using CPUs instead of GPUs. But overall, you'll still be able to learn how to code these how to code these deep neural networks using TensorFlow. Now, for wide versus deep, when it comes to neural networks, when you use the term wide or the word wide, then that refers to a neural network that has a single hidden layer, at least most often. So a wide network may have a single hidden layer with a lot of different nodes, so it's a wide network. Now, the reason to use those can be because perhaps your data overall doesn't have a lot of complexity to it, so you don't need a deep neural network. But also, in some cases, you can use a wide network to approximate the functions that a deeper model will learn, to approximate the relationships by having many nodes. Now, in deeper models, in this image, we can see here that this would be just an example of a deep network that is learning to recognize faces. So early on in the network, the nodes are just learning very small patterns. They're like, for example, here we have patterns of local contrast. So it's just kind of learning small edges that it may find in the image. And as you propagate through the network forward, then each successive layer is going to kind of accumulate all of these different patterns that are being learned in previous, or aggregate I should say, all these different patterns that are being learned in the previous layers to come up with more like larger, more generalized abstractions. So from these patterns of local contrast, ultimately they combine to learn facial features. So it'll learn eyes, noses, mouths, things like that. And then toward the end of the network, we're actually learning whole faces, whole heads of people. And so that's kind of just an overview of how deep models work, whereas wide models, they'll just be kind of approximating that functionality. Now, for use cases for deep learning, there are many, and we have a decent amount of them listed here. Let's start with audio. So for audio, we can do things like voice recognition, sentiment analysis, so that would be the actual sentiment of the speaker. Are they angry? Are they calm and soothing? Things like that. And then flaw detection, that would be for things like detecting flaws in machinery, like turbines or jet engines, things like that. And not just detection of the flaws, but perhaps classifying just what the flaw is based on the sounds that are there. For text, there are a lot of different things there. Again, sentiment analysis. We have the ability to classify the topic or theme of a particular document. And then there's fraud detection. So does that document actually belong to the person it's supposedly written by? Things like that. And threat detection, that one, I suppose you would have to use your imagination there, but perhaps, is a document actually threatening to a particular corporation or an individual for some reason? And if you look in the lower right, actually, should have mentioned this for audio, there's a spectrogram there. So with that, moving from left to right, that is the time of the audio, like increasing time. So the beginning of the audio starts at the left, ends at the right. And then you have higher and higher frequencies as you move up the spectrogram. So it's really an image of a whole audio recording. So that's an example of how a deep neural network may be able to use audio to learn just like it would for images. So in this case, you can learn patterns in audio. Now for images, most of you are going to be familiar with that. We have things like facial recognition, object classification or detection, and to some degree you may combine it with other techniques to do object localization. And then there's machine vision, which is kind of a generalization of a lot of these things. So for example, automated vehicles, they use machine vision, so they'll have a collection of cameras that feed into a model that can learn to detect different objects on the road or off to the side of the road, and as well as the lines that it must stay between. So that's kind of where computer vision applies to deep learning. All right, and now for our refresher on the vanishing gradient problem. If you recall from an earlier tutorial where I covered the vanishing gradient problem, at least briefly, overall the vanishing gradient problem is the inability for a network to learn at earlier layers, and that arises from things like the sigmoid function, which you can see here as the larger red curve on the left, and then its derivative, which is the shorter green curve at the bottom there. So the problem is, with earlier layers, you end up with very small values that are multiplied through the backpropagation. So backpropagation is what gives us values to update the weights. So for an earlier layer, you're multiplying small values, values that are smaller than 1, for all of the different layers. And so that number that you multiply ends up being added or subtracted to or from the weights. So if you have many small numbers, really small, multiplied together, you get effectively 0. So you're really not adjusting the weights at all, so they're not learning. And you can see this because on the sigmoid function, and that would be our activation function, for example. If you're very far to the left or the right on that curve, then its derivative is effectively 0. So we're multiplying a whole bunch of small numbers together, getting 0. And there's no learning happening in those earlier layers. So that's the vanishing gradient problem. And on the right here, we can see two different examples. The top function is the ReLU, or the rectified linear unit. That is one solution to the vanishing gradient problem, but it isn't perfect. With this one, you either have a derivative of 0 or 1, depending on what the activation function's value is. So if the activation function is negative, then your derivative is just 0. And if it's positive, then it's always 1. And so in that case, that helps to eliminate the vanishing gradient problem to some degree. But because of those 0 values that you can have, you may end up with dead ReLU units. And so in that case, they basically never update. So again, we're duplicating the problem to some degree. On the bottom, that is the leaky ReLU. So for this, instead of just setting it to 0 if if the activation value is negative, then it just gives it a smaller value, smaller than 1. So for example, it may be 0.5. And so that overall can help to alleviate the problem quite a bit. In the networks that we're going to be constructing, we're just going to use the standard ReLU, because overall they work pretty well. Alright, so with that out of the way, let's go ahead and move on to the code. Alright, so now with the code, a lot of this code I've already written, or really all of it I've already written to save us on time, and we'll go over it in detail. As usual, just go ahead and import TensorFlow and NumPy. And one other thing that you'll want to do is from collections import ordered dict. It's just an ordered dictionary that's going to help us out. You could use lists instead, but this way we get to actually have some names to go along with it. Overall, it's just going to be make things easier for us. In this case, what we're going to do is we're kind of modifying the code that we used for the convolutional neural network that we built. But this time what we're doing is A, we're going to be using dense layers, and B, we're going to be actually constructing a model that we can have more control over. On the convolutional neural network that we built, the layers that we added to it, they were just fixed. So it was a fixed architecture that the user has no control over. You'd have to actually change the code itself in order to add more layers or change the number of nodes. So in this case, what we're going to do is we're going to create some functions to kind of help us out. We have one that is going to be the create dense layer. So this is one that we'll call in order to create dense layers based on whatever the user calls. And then we also have create dropout so that we can add dropout to anything after a dense layer. Usually we would use that on a convolutional neural network, but no big deal. It's still going to help us out here. So for the create dense layer, we need a number of arguments. Inputs, that's going to be essentially whatever the previous layer is. So we're going to add that so that this can operate on that previous layer or from the outputs of the previous layer. And nodes, that's going to be how many nodes we want in this particular layer. Activation, we're going to set that to none as a default. And if it is none, then it's actually just going to be essentially no activation. So it's really just going to be totally linear. And then for dropout, we're going to add this so that when we're creating layers, we can actually add dropout to the end of that layer and that'll just make it easier for us. So set it to none so that if it is none, no dropout will be added, and we'll see how we'll handle that later. So for this function, all we need to do is return and then tf.layers.dense, and for this we need to set inputs units to end nodes and then set our activation function. So we can pass in custom activation functions if we want to, or not just custom, but also whatever activation functions are available through TensorFlow. Now for the create dropout, again we need inputs. That will be whatever layer it follows again, so that'll be the outputs from the previous layer. Rate will be the rate of the dropout. So that's going to be, for example, if rate is set to 0.4, which is a value that we'll use, then that means that there's a 40% chance of any given weight being dropped. So on average, we'll have 40% of the weights dropped from a particular layer. And then mode. The mode we need to pass in because that is the mode of our model. So for example, with dropout, we only want to use dropout when we're in training mode. Whereas if we're not in training mode, like if we're in predict or evaluate, then we do not use dropout. And so in this case, we're going to return tf.layers.dropout. Again, inputs equal inputs, rate equal rate. And then for this last argument here, we just say training equals, and then we do mode equal tf.estimator.modekeys.train. So what this says is training equals true or false. So it equals true if we're in train mode and false if not. And this just tells TensorFlow whether or not to activate the dropout. All right, so with those functions out of the way, let's move on to the model function itself. So in this case, this is really just a modification, or this part right here, as I mentioned, this is the modification to our convolutional model. So as before, we have features, labels, mode, and then params. This is where we're going to pass in any user-defined parameters. So if you'll recall, it very specifically needs to be called params with TensorFlow, because that's how we're going to pass things in. And it looks like I've re-imported orderDict from collections. That's fine. You may choose to just leave it in the model or in the function. That way you know that it's always imported. You don't import it externally. So now the layers dictionary is something we're going to create to hold our layers. So we're going to call it layers_dict, and we're going to just create an empty orderDict. Now the reason for using an ordered dictionary instead of a standard dictionary is that way we can actually keep track of the order of our layers that we're storing inside of it. Whereas with a standard dictionary, order is not preserved. Things just kind of get mixed around in there and you only call them specifically by their keys. So the first thing that we're going to do is we're going to store the input layer, which, if you'll recall, is just our features. So in this case, we're going to say that it's features x, and also remember that we pass in our features as a dictionary in TensorFlow, or at least in this model. So let's move on to now creating the layers. These are the user-defined layers that we're going to create, and we're going to create those using a loop over the layers portion or the layers values from our params. So we're going to enumerate, that way we can keep track of the actual layer number itself. And the very first thing that we're going to do is do the layers inputs. So in this case, we're going to say layer inputs equals, and we're going to wrap a list around our layers dictionary. That way we can actually subscript it. You can't subscript an ordered dictionary, so we're going to turn it into a list. So in this case, we're going to get the very last value from our ordered dictionary. That's our last layer. And so that way we actually have inputs for the next one. This portion right here, the if layer equal params layers and then the subscript -1, what this is doing is we're just checking to see if the current layer that we're processing, that we're creating, is the very last layer. If it's the last layer, then that means we're going to call it logits. So that is basically our output layer. Otherwise, we're going to say that its key is layer plus whatever the layer number is. So it may be layer 0, layer 1, etc. And so with the key set, then all we have to do is add a new layer to our dictionary. So in this case, it's going to be layers_dict key, and then it is equal to, and in this case, we're going to create dense layer. And right here we have our layer object. As we will see, we're passing in a dictionary of parameters for this that the user defined. So the double asterisk here, it's going to extract all those to use them as keyword arguments, using the keys as the actual parameter or argument names, and then the values as, of course, the argument values. So this is going to create our dense layer. So if we go back up and look at that, then it would extract things like inputs, and this is why we added the inputs to our layer dictionary right here. That way it knows which layer to input to it. And then the user-defined portion would be endnodes, the activation function, and dropout. All right, so at this point, this creates a dense layer and adds it to our ordered dictionary. And now, if there is dropout in the layer, so basically if it's not none, if somebody defined the actual dropout value, so if there's layer dropout defined, then it's going to add a dropout layer. So we're going to have dropout, and then this isn't and this is not a 1, it's an L. So dropout L and the layer number. That way the name is kept track of for the particular layer number. And so then we call the create dropout function. And again, we need to wrap a list around our layers, and this is going to pass in the inputs. So if you look back up here, we have inputs for our dropout. That's what we're passing in here. It's the very last layer created in our ordered dictionary. And we're going to set our rate, and this is the dropout value in our layer, and set mode equal mode. All right, so at this point, there's a print function here. This is totally unnecessary. It's just there to see the structure of the layers that were user defined.